Now we'll look at one of the uses for the mean value theorem. And the first one, which uses the mean value theorem, would be in graphing functions. Okay, so to graph, what we need first is a definition. We're going to start with increasing, decreasing. So for x1 less than x2, if f of x1 is less than f of x2, then f of x is increasing for all x1 and x2 in the interval that we're talking about. So for an example, here's x1 is smaller than x2. F of x1 is smaller than f of x2, then this function increases. And the same thing holds for x1 larger than, well, we'll just switch one of those. If f of x1 is bigger than f of x2, then f of x is decreasing for all x in the interval. Okay, so what does it mean to be increasing, and decreasing? If we look at a picture, let's take this graph. Right here, as you travel left to right, the graph increases. So right here, f is increasing, and then look what happens. You have a horizontal tangent line, and then f is decreasing here, all the way to here, and then you get a horizontal tangent line, and then it increases after that. So let's look at an example, an easy example. Let's take y equal x squared, and y prime is 2x. What we're going to do is find out where there's a horizontal tangent line by saying the first derivative equal to 0. So that just gives us x equal to 0. When you divide both sides by 2, and if you look at the graph, this is a parabola, and at 0 here, there's a horizontal tangent line. Let's make it red. Horizontal tangent line. And on this side, if we look at the slopes of the tangent line, the slopes of the tangent line are negative. So f prime is negative and f is decreasing. F is going down because you always follow the graph left to right. And if you look over here and you draw the tangent lines, the slopes of the tangent lines are positive. So over here, f prime is positive and f is increasing. So this is called the first derivative test, or, well, it leads us to the first derivative test. First off, f has to be differentiable. You need to talk about first derivative. If f prime is greater than 0, then f is increasing. If f prime is less than 0 or negative, then f is decreasing. And let's prove that using the mean value theorem. Remember the mean, or the average, which was this, equals f prime of c for some c in x1 or x2. So let x1 and x2 be points in the interval I, where let's let x1 be smaller than x2. So let's talk about signs. If x1 is larger, this x2 is larger, and you subtract x1, then that means 0 is less than x2 minus x1, or x2 minus x1 is greater than 0, and that means it's positive. So that means this is positive. F prime of C is positive. We'll prove A. This is A. So if F prime is greater than 0, then this is positive, since F prime is greater than 0. And that means if it's equal to a positive number, the denominator is positive. That means this has to be positive. So F of x2 minus f of x1 is greater than 0, which implies f of x1 is less than f of x2, which implies f is increasing. And you do the same thing for decreasing. So for a fraction to be positive, both the numerator and denominator either have to both be positive or both be negative. And so that's one use of the mean value theorem. That's why we talked about the mean value theorem earlier in the last section. Okay, for an example of this, let's pick x cubed minus 3x, and y prime is 3x squared minus 3. And if you set that equal to 0, that's where you have horizontal tangent lines. So we get x equal plus or minus 1. Now, we don't know if it's a max or a min. We know this is a polynomial, so it's continuous and differentiable. But we don't know if it's a max or a min. Okay, so what we're going to do is test the first derivative. So here we're going to test the first derivative. If we plug negative 2, let's pick negative 2. Negative 2 into the first derivative is positive. 0 into the first derivative is negative, and 3 or 2 into the first derivative is positive. So if f prime is positive, f is increasing. Negative, it's decreasing, and positive, increasing. So that tells us about our graph. So if we get our points on this graph, if we plug negative 1 into our original function, we have negative 1 plus 3 is 2. So we have negative 1, 2. We'll have 0, 0. And we plug 1 in and we get negative 2. So it's increasing up to this point. F increases. It decreases. Let's see. We need to decreases here and then increases. We know it's smooth because it's a polynomial. Okay, so this tells us something. Let's formalize this, and let's call this the first derivative test. And in the first derivative test, we'll say C is a critical point, or critical number. Now, review that. That's where f prime is undefined or equal to 0. That's where that happens. So you either have a vertical tangent line or a break, or you have a horizontal tangent line. Okay. If f prime changes from positive to negative, that means first it's increasing and then it's decreasing, then C is a local max. If f prime changes from minus to positive around C, then C is a local min. Now, how do you know that? Well, that means if f prime's negative, you're decreasing. If f prime's positive, you're increasing. So you get a low point. If no sign change around C, C is neither a local max or a local min. Okay, so we saw in our other example, in the last example that we did, let's go find it. Right here, let's go back, that where f prime was increasing, f prime is positive. Let's look at this line right here. F prime changes sign from positive to negative, so increasing to decreasing. This point is a local max. And then decreasing to increasing, or positive, it's a local min. And you can see that on the graph. This is where you have horizontal tangent lines. Here you have a max, local max. Here you have a local min, decreasing, then increasing. All right, let's talk about the second derivative, because this gives us more information. And let's just start with the fact that if f prime is positive, f increases. So what happens about the second derivative? The second derivative is positive, then f prime is increasing. Now, if your slopes are increasing, so they get flat, so they go from, say, a half to 1 to 2, then your graph goes like this, and it's concave up. So if f prime is positive, it's concave up. That's just one example. If f double prime is negative, I meant double prime, then f prime is decreasing. So if your slopes are decreasing, so if they're real steep and then they're decreasing, then it's concave down. If f double prime is negative, then we get it's concave down. Okay, let me go back and get the slopes for this. Suppose this is like -1, this is -2, say this is -3. You see they are decreasing. The slopes are decreasing. Okay, so concave up is where f double prime is positive, and it could either be like this or like this, because here f decreases and here f increases. Or you could get something that's concave down. F double prime negative, this is where f is increasing and f is decreasing. So those are your four cases. The point where the curve changes concavity is called the inflection point. So here's an example. That's an inflection point because here it's concave down, concave up, inflection point, concave up, concave down. This is concave down. This is concave down. It doesn't change. That's not an inflection point. It has to change concavity around that point to be called an inflection point. Okay, let's try this example. Let's take the first derivative. Set it equal to 0. Factor. And we get x is 2 and negative 1. These are the critical points, or critical numbers. That's where possible max and min occur, local max and min. You have to test them. You have to do the first derivative test to tell what they are. So here we go. We do a number line. We plug values into f prime, and that tells us what f is going to do. So if we take, say, a negative 2 and plug it into f prime, we get a positive number. I don't care what that number is. It's just all we want is a sign. Pick 0. I always try to pick 0 because that's easy. It's going to be negative. If we pick 3, it'll give us a positive result. So what I'm doing is taking these, they're called test numbers, and substituting them back into any one of these three, the first derivative. So that tells us that f is increasing, then it decreases, then it increases. So what do we have? If it increases, then decreases, this is a local max. It's a high point. If it's decreasing, then increasing, we get a low point. So we have a local min. So that's the test that you have to do to decide if your critical points are maxes and mins. They don't necessarily have to be. Then we go back and take the second derivative, and we set that equal to 0. Where it's equal to 0 is going to give us the inflection points. Actually, it gives us the possible inflection points, and you have to test them to make sure they are. So here's the test, and I test them, and I take a test number on the left, so let's pick 0, and a test number on the right, and plug them back into the second derivative. It's negative. When I plug in 1, I get a positive value. So on this side, it's concave down, y is. On this side, it's concave up. So this is an inflection point since a change of concavity occurred. So let's put this all together in one picture. Now, you probably won't see this in the book, but I really, really like to do it this way. I put in all of my points that I got. So critical points and inflection points. And then you test them into y prime. It tells you what y does. You plug them into y double prime, and that tells you what y does. And then you get the picture of each interval. Okay, so we're going to start out with, say, negative 2. These are our test numbers, 0, 1, and 3. Now first we're going to plug it into y prime. And we get positive, negative, negative, positive. This says y is increasing, decreasing, decreasing, increasing. The second derivative is negative on the left of 1/2 and positive on the right of 1/2, plugging your test numbers into the second. Okay, so you put your critical points, inflection points on the number line, then you pick test numbers, You plug them into y prime and y double prime, and that tells you what y does. So concave down, concave down, concave up, concave up. So increasing concave down is like that. Decreasing concave down is like that. Decreasing concave up looks like that. Increasing concave up looks like that. So then I go to my final picture. No, then I get my points. Okay, let's just make this step 5. I get my points by plugging them back into y. So when x is -1, then y, when I plug it back in, is 13. So I have the point -1, 13. When x is 2, I have y equals 16 minus 12 minus 24 plus 6. And when y is 1/2, when x is 1/2, y is 16 minus, 1/4 minus 3/4. It's going to be -1/2. And I'm ready to sketch it. So -1, 13. 2, -14. 1/2, -1/2. And it's this. We just play connect the dots now. This and this. Nice and smooth. So that's an inflection point. This is the max. This is the min, locally. There's another way to tell whether things are maxes or mins, points, whether points are maxes or mins, and that's by the second derivative test. And f double prime has to be continuous near the point C, and C is a critical point. So that means either f prime is undefined or f prime is 0. If C is a critical point, you plug it in to the second derivative. If the second derivative is positive, then C is a local max. Local min. Because that means if f double prime is positive at that point, that f is concave up at C, and that's a min. And if f double prime at that point is negative, then C is a local max, because if it's negative, then if the second derivative is negative, then f is concave down, which looks like that, and C you get a max. So let's try it in this example that we just did. We're going to do y double prime of our critical points. So plugging -1 into our second derivative is going to be -12 minus 6, which is -18. So y double prime is negative, implies that -1 is a local max. And if I do y double prime of 2, that was my critical point, that will give me 24 minus 6 is 18, which is positive 18. So y double prime is positive, implies 2 is a local min, because if it's negative, it's concave down, so you have a max. If y double prime is positive, your graph is concave up, so you have a min. Now, you don't do that for the inflection points. You just do that for your, these things here are called critical points. And the second derivative tells us whether we have a max or a min. Okay, so hopefully you can see how we can use these derivatives to graph.